Alright, thanks for watching, and today I want to evaluate a very crazy integral called the Vardi integral. And I love this name, by the way. It sounds like Vivaldi and Lombardi put together to get Vardi's integral. Alright, what is that integral? So lots of ln degenerates here. It's the integral, I guess step one, what do you want to calculate? The integral from pi over 4 to pi over 2 of ln of tangent of x dx. Oh, ln of ln. And I probably forgot a parenthesis here. First of all, why is this defined? Well, if x is greater than pi over 4, then tangent is greater than 1. So ln of tangent is greater than 0. And that's what we need for the outside ln to be defined at. So, first of all, we would like to simplify this integral a little bit. Namely, let's use a u substitution. Let u be ln of tangent of x. So let's substitute this inner tangent. So release your inner tangent, and we get du is 1 over tangent of x secant squared of x dx. And look, this involves tangent, so it would be nice to write secant squared in terms of tangent, but we can. So it's 1 over tangent of x, 1 plus tangent squared of x dx. And that's just 1 plus tangent of x plus tangent squared over tangent, which is tangent of x dx. And why is this nice? Well, look, u is ln of tangent of x, so tangent of x is e to the u. So this is e to the u, this is 1 over e to the u, so e to the minus u plus e to the u dx, and this equals e to the u plus e to the minus u dx. In particular, dx is 1 over that du. Lastly, just the endpoints. So u of pi over 4, well, that's ln of tangent of pi over 4, which is ln of 1, which is 0. And u of pi over 2 is ln of tangent of pi over 2. And here we mean the improper integral. So really limit as x goes to pi over 2 from the left. So it's really tangent of pi over 2 minus, so infinity, and ln of infinity is infinity. Good. Once we use this u substitution, we just get the following. So we get that the integral becomes integral from 0 to infinity, ln of u over e to the u plus e to the minus u du. And we would like to use power series, in particular our best friend, 1 over 1 minus x. So let's multiply both sides by e to the u, e to the u, e to the u du, and we get integral from 0 to infinity e to the minus u ln of u 1 plus e to the, we multiply by e to the minus u, so 1 plus e to the minus 2u du. And the nice thing is, this junk here becomes 1 over 1 minus this, so we can use a power series. So the second step is just to write it as an integral from 0 to infinity e to the minus u ln of u 1 over 1 minus e to the minus 2u du. And now this just becomes, remember our best friend, 1 over 1 minus x is the sum of x to the n. And in particular, use that with x is e to the minus 2u, which is in the appropriate range. So it is in the interval of convergence. So it's integral from 0 to infinity e to the minus u ln of u times the sum from n from 0 to infinity of minus e to the minus 2u, sorry, minus minus 2u to the n du, which you can write as integral from 0 to infinity e to the minus u ln of u sum from n, yk, I'm still stuck in another video, and from 0 to infinity of minus 1 to the n e to the minus 2nu du. And of course, just like as usual, the trick is just put this inside and use a Fubini kind of argument and assume again that it's valid. So let's interchange this sum and this integral. Okay, so let's Fubini that and let's hope it simplifies. So, step 3. The integral becomes the following. So after Fubiniing it, Fubini. By the way, speaking of Fubini and like Mario and Luigi, I just found out Super Smash Bros. Turned 20, and it makes me feel a bit old. Yeah, because I grew up with Super Smash Bros. So it's like. Anyway, but Fubini is older than that, so that doesn't worry me for some reason. But so we have the sum from 0, so our integral equals then the sum from 0 to infinity of minus 1 to the n, integral from 0 to infinity. So we still have this ln of u, and remember we had this e to the minus u and e to the minus 2nu, which we can put together as e to the minus 2n plus 1u du. And now, again, in order to clean this up a little bit, let's just use a u substitution. So let v be 2n plus 1u. Then we still get sum from 0 to infinity of minus 1 to the n, integral, multiplying by a positive number doesn't change that, and we get, if you want, e to the minus v, and then ln of, so if v is 2n plus 1u, u is v over 2n plus 1, and then dv is 2n plus 1u, so du is dv over 2n plus 1. You see, it's a very deviant integral, because it's dv. Anyway, and then, of course, you see ln of a quotient, so let's just use ln of v minus ln of 2n minus 1. So that's the sum from n from 0 to infinity of minus 1 to the n over 2n plus 1, integral from 0 to infinity e to the minus v ln of v dv minus 1 to n of 2n plus 1, integral from 0 to infinity of e to the minus v ln of 2n plus 1 dv. All right, and now what's the next step? Well, notice this term here doesn't involve n at all. In particular, this term we can pull outside of the sum. So that's okay. And notice also if n equals to 0 here, ln of 1 is 0, so it doesn't involve the sum at all. And then also, let's see, also here, this term doesn't appear, doesn't depend on v at all, so we can pull it out, and then we're left with the integral from 0 to infinity of e to the minus v, which is just 1. So this integral is 1, and then all we're left with are 3 terms, Namely, let me write this here. So we have, first of all, the integral from 0 to infinity, e to the minus v, ln of v dv. That's our term A. Then, the sum from n from 0 to infinity of minus 1 to the n over 2n plus 1. That's our term B. Okay. And lastly, this term here, the sum from 1 to infinity, because this term is 0 at 0, of minus 1 to the n plus 1 over 2n plus 1. So plus the sum from 1 to infinity of minus 1 to the 2n plus 1 over 2n plus 1 times the term ln of 2n plus 1. And this is our term C. So all we need to do is calculate the following three terms. This integral here, the sum here, and that sum here. Okay? Alright, now, this integral I will do in another video. So, but let me sort of sketch what we have to do. So the rest of the video is just to calculate those three terms. So step 4. So A, which is the integral from 0 to infinity of e of minus v ln of v dv. Either, so see another video, I'll do that, or if you want, that's, if you maybe know this result, you can use a substitution. I guess w, if on w equals to e of minus v, then dw equals to minus e of minus v dv. So we get in the end integral from 1 to 0 ln of minus ln of w minus dw, and that's just equal to the integral from 0 to 1 of ln of 1 over w dw. And as I said, either you know this result or see another video that I post. Turns out this integral, interestingly enough, is equal to minus the Euler-mascheroni constant, which you remember, it sort of calculates how ln of n is different from the harmonic series. So ln of n minus the sum from k from 1 to infinity of 1 over k. This sum, even though the two things diverge, sum from 1 to n, and you take the limit as n goes to infinity, turns out this sum, even though the two terms diverge, the difference converges, and it turns out, I think that term is just equal to minus the Euler-mascheroni constant. So it's a very impressive result. So, what have we done? The first term equals to the Euler-mascheroni constant, and now let's see what B equals to. Oops. So if you want to grab some popcorn, let me turn on the lights again. Perfect. And I'm back. Again, sorry about that. It's just, this room is amazing, but it's just the lighting that's a problem. But at least I think the whiteboards are the best in the whole room. In the whole building, that's what I mean. Alright, fifth step. So, B is equal to the sum, remember, from 0 to infinity of minus 1 to the n over 2n plus 1. Now, it turns out there's a very nice power series which relates, I think, odd terms. So I think it's minus 1 to the n. Yeah. Sum from n from 0 to infinity of minus 1 to the n, x to the n over 2n plus 1. I guess x to the 2n. Maybe. Let me check on my wonderful sweater. The Black Pen gave me this sweater of tables of integrals, and the one we want to use is the one for arctangent, which I'm glad I checked. So it's the sum of odd powers of x. So 2n plus 1 over 2n plus 1. This thing equals to arctangent. I want to wear it, but it's really hot today. It's weird. It's the end of January in Southern California, and I'm walking in shorts. It's amazing, by the way. But yeah, so this thing equals to arctangent of x. In particular, if you let any x equals to 1, it's precisely what we want. So that sum becomes arctangent of 1, which is pi over 4. Wonderful. We have the second step, and now you might be, oh, it's not that bad. We just have one more series to evaluate, but turns out this is the hardest one. So step 6. So C, which again is the sum from 1 to infinity of minus 1 to the n plus 1 over 2n plus 1 ln of 2n plus 1. All right, now we need to use another series which I'm not very familiar with, and I don't know why it works, but it's the following. It's what's called the Kummer series. And Kummer in German means sorrow, so it's a very sad series. But what does it say? It turns out what it says, it's some expansion of the gamma function in terms of a series. So it's pretty useful. And it says the following. So Kummer series. There's actually this beautiful word in German. It's called Liebeskummer. It's like when you really love someone and you miss that person. Let's say that person is on vacation or something. Then you have Liebeskummer. It's like the sorrow of the heart. Okay, but what does that have to do with math? So the Kummer series says, if you take the gamma function and you take ln of that, that equals to minus z of the Euler-mascheroni plus ln of 2 pi minus 1/2 ln of sine of pi z over pi plus 1/2 Euler-mascheroni plus ln of 2 pi plus 1 over pi and sum from n from 1 to infinity sine of 2 pi zn ln of n over n. Holy moly, okay? So, and you say math is not complicated. So it's a very complicated series, but that's nice. It takes the gamma function and evaluates it in terms of this series here, plus some terms that involve the gamma function. And notice, this is very nice because we have ln of n over n. And remember here we want ln of 2n plus 1 over 2n plus 1. So we just want odd terms, and that's why it's good to make this term such that n becomes odd. And the way to do this is simply let z be 3/4. I think that's the term that makes this odd. So if you have z equals to 3/4, then ln of, we get gamma function of 3/4 equals to, so minus 3/4, Euler-mascheroni, minus 3/4, ln of 2 pi, minus 1/2 ln of, so sine of 3/4 pi, so 3 pi over 4, that's still positive, so it equals 1 over square root of 2. But with that pi, so pi square root of 2, and then plus. So 3/4 times plus 1/2 is, I think, 3/2. I don't know why it was 1/2, but plus. Let me double check something. Oh, okay, so plus 3/2 Euler-mascheroni plus wait, 3/4. No, sorry. There's no z here. I don't know why I was thinking. So plus 1/2 gamma plus 1/2 ln of 2 pi. And the stuff that we want, so plus 1 over pi sum from 1 to infinity of, let's see, sine of 3 pi over 2 n ln of n over n. And notice, what happens if n is even? If n is even, let's say of the form 2k, then this is sine of 3 pi k, which is 0. So in particular, what we need n is odd. So it turns out this whole sum just transforms to sum from k from 1 to infinity, sine of, if n is odd, this just becomes minus 1 to the k plus 1. I think so. And ln of 2k plus 1 over 2k plus 1. Which is precisely what we needed. So I'll raise the whiteboard in a second, and then you'll see that, in fact, this is what we needed. Okay, so this is precisely the same form. And so we can just simplify this a little bit. So let's see, ln of gamma function 3/4. So I think the Euler-mascheronis, they simplify. So we have minus 3/4 gamma, this term, plus this term becomes minus 1/4 gamma. So minus gamma over 4. And then we had, so minus 3/4 ln of 2 pi plus 1/2 ln of 2 pi. Let's see what that equals. This is minus 1/4 ln of 2 pi. This thing here, ln of 1 over something, is minus ln of that something. With that minus, it becomes a plus. So plus 1/2 ln of square root of 2 pi. And the sum that we want, 1 over pi, sum from k equals to 1 to infinity of minus 1 to the k plus 1 ln of 2k plus 1 over 2k plus 1. Now notice, this suspiciously looks a lot like ln of pi, so let's simplify that further. So this thing is minus 1/4 ln of 2 minus 1/4 ln of pi, okay, plus 1/2 ln of square root of 2, which is actually 1/4 ln of 2, plus 1/2 ln of pi. And lo and behold, this simplifies, and we get in the end 1/4 ln of pi. So now, solving for this term, I feel I'm turning into a blue pen, red pen or something, because I'm using blue pens and red pens now. So it's sort of a mix between 3 blue, 1 brown, and black pen, red pen. So now we can solve this. So we get our thing here, sum from k equals to 1 to infinity, which is what we want, by the way. So that's C, equals to minus 1 to the k plus 1 ln of odd terms. So 2k plus 1 over 2k plus 1 equals, so pi times this, pi ln of gamma function of 3/4 plus pi times pi over 4 mascheroni. Sounds like mascarpone. Very good. So minus pi over 4 ln of pi. Wonderful. This was C, and then we had other terms A and B, and now we're ready to actually give the answer for Vardi's integral. So let's see, maybe I You can just put in the last one. So step 7. So what did we try to evaluate? I keep forgetting. So our integral, yes, integral from pi over 4 to pi over 4, ln of tangent. Remember, it was equal to 3 terms. One was this weird integral with the Euler-mascheroni. The other one was just this arctangent of 1. And lastly, we had plus the sum we just evaluated. So in the end, we get, so this term was minus Euler-mascheroni. This one was arctangent of 1, which is pi over 4. And the last term was, well, the thing we just evaluated, pi over 4 gamma plus ln of, so plus pi over 4, sorry, let me just think. Oh yeah, the stuff we just evaluated, so which is, so pi ln, okay, plus pi ln of gamma of 3/4 minus pi over 4 ln of pi. And lo and behold, notice what's happening. The bad terms, in other words, the Euler-mascheroni constants, they actually disappear. Which means our answer doesn't even involve Euler-mascheroni at all, which is interesting, right? It was like this little helper which we forgot about. It's like when you Super Mario and at the end, to get at the end of the level, you just leave Yoshi alone. And Yoshi is like, what the hell? What, you know, what have you done to me? Okay, so we have this, and then we're just left with, you can simplify this a little bit. So that's pi over 4, and then 4 ln of Euler-mascheroni, no, gamma function, no more Euler-mascheroni, minus ln of pi, which you can write as pi over 4 ln of Euler-mascheroni of 3/4 to the 4th power over pi. Now, if you're satisfied with this, you can just stop watching, but if not, there is actually a clean simplification of this, because it turns out, so let's clean this up. I have done a video on this, but there's this Euler's reflection formula, which actually tells you that gamma function of z times the gamma function of 1 minus z is pi over sine of pi z. In particular, gamma of 1/4, so if you let z be 1/4, gamma of 1/4 times gamma of 3/4 is pi over sine of pi over 4. Sine of pi over 4 is 1 over square root of pi, so this becomes pi times square root of 2. And so, indeed, what we get then is gamma of 3/4, or not that, we want to use this pi, so that's equal to pi over 4 ln of, so let's see, gamma of 3/4 squared, gamma of 3/4 squared, over, let's see, let's do a pi squared here. So let me just think, how do I simplify that? Yeah, so in particular, let's see, gamma of 3/4 equals to pi square root of 2 over gamma of 1/4. Okay, so we have this. And then in particular, gamma squared becomes now pi over 4 ln of gamma of 3/4 squared. Okay, now gamma of 3/4 squared then becomes 2 pi squared. And we still have this pi, and we have gamma of 1/4 squared. And so one of the factors of pi disappears, so this pi cancels out with this pi, and then if you want that equals, let's see, where do you have space? Well, let's just make some space. At the end, this whole gibberish becomes pi over 4 ln of, so gamma of 3/4 over gamma of 1/4, a square root of 2 pi squared. Which, last simplification, I promise, you can write in the way that I saw it, at least in the answer, pi over 2 ln of gamma of 3/4 over gamma of 1/4 of square root of 2 pi. And what is this? Again, it's the integral of from pi over 4 to pi over 2 of ln of tangent of x dx. Ta-da! All right, I know this was tough, but I think that was a very, very exciting adventure into series and integrals, because we started with a u substitution, used some power series, used a sprinkle of the Euler-mascheroni, which then we forgot about. We used this weird Kummer series, which I don't know where it comes from, and then we just wrote our answer in terms of gamma functions and square roots, just to clean it up. Alright, so I hope you like this integral adventure. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.